In this presentation, I'm going to talk about scalable, privacy-preserving, distributed, extremely randomized trees for structured data with multiple colluding parties. First, I'm going to talk about the problem. Then I will discuss briefly distributed, extremely randomized trees. Then I will proceed to secure multi-party computation for privacy-preserving distributed ERT. And then I will discuss the limited participation of parties for selecting the best candidate decision node at every round of learning process. Finally, I will talk about the evaluation and conclude the presentation. So for the problem, our problem is that the data in many scenarios are distributed over an arbitrary number of parties. These parties could be hospitals or patient mobile phones or other personal devices. But these parties cannot share their data to each other or to another center for performing the analysis because of the privacy and legal concerns. But we need, in our problem, we need to learn classification models from this data, which is structured and horizontally partitioned, without having access to this data, without having a direct access to this data. So the algorithm that we want to use for learning classification models is ERT algorithm, or extremely randomized trees algorithm, which is a state-of-the-art tree-based ensemble learning method, which is robust to overfitting, but it is for scenarios in which data is stored in one center. But in our scenario, the data is distributed over multiple parties. And the parties cannot share their data with one center for learning from this data. So in ERT algorithm, when the data is in one place, we have several candidate decision nodes at every step, and we want to select the best among them. We select the best candidate based on the score or information gain for that candidate decision node. But what we do in centralized version is that we classify the data with candidate decision node and check the impurities of labels for data records at each branch. And with that, we can calculate the information gain and choose the best decision node. But when we don't have the data in one place, we need to do this classification locally at each party, and then sending the information about the labels after classification to the to a center or the mediator for selecting the best candidate decision. So with distributed ERT algorithm, we preserve the privacy of record owners to some extent by not sharing the data values of attributes to other parties or to the mediator. But still, there is a risk for revealing some sensitive information about the patient. For instance, if one party has only one record on it, and if the candidate decision node asks about a sensitive information, like asks about a disease like HIV, so when the party classifies the record with that candidate decision node and returns the partial result to the mediator can identify if the record owner or the patient was diagnosed with HIV or not. So for addressing this, we need to use secure multi-party computation. The first phase for doing the computation is sharing the seeds for the random function. Each party needs to share a unique ring and a unique seed with other parties. The seed is unique among for each two pairs. The seed will be unique, and the seed that P1 sends to P2 is different than the seed that P2 sends to P1. So after after the initialization, every party sends n-1 seeds for random function to other party, in which n is the number of parties, and it also receives n-1 seeds from other parties. Every party needs to generate a random mask or a random number based on based on each received random seed, and then the party aggregates those random masks, and after aggregation we have random sum other. And every party also needs to generate random numbers based on the seeds that the party sends to other parties. After generating those random numbers, it aggregates them, and we have it as a random sum self. So every party needs to aggregate its random sum others plus its secret value and deducts the random sum for self. So this would be the value that each party will share with the mediator. And the mediator, after receiving this value, will, from all the parties, aggregate them all. And by aggregating them all, these random sum selves will cancel out with these random sum others for all parties. And finally, we will have the summation of these secret values. But the other part of the k-PPD-ERT approach is to limit the participation of parties in every round of secure aggregation or every round for selecting the best candidate decision node. So before, all the parties would participate in the process for selecting each candidate decision node. But we propose that we can limit the proportion of parties participate in each round. So by limiting this in the evaluation section, we will see the results for reducing the overhead and for the classification performance. So for evaluating the data mining approaches, we have three criteria: classification performance, overhead, and privacy. So for the secure aggregation technique that we adopt, we check the overhead and privacy of our approach and compare it against the Shammir's approach, which is the adopted approach in distributed ID3 algorithm. We also compare it with distributed ERT, which employs no secure multi-party computation technique. So regarding the Regarding the communication overhead, our approach has the same overhead as employing no SMC approach. But our approach is from order n, but Shamir's approach is from order n squared. So our approach has much less communication overhead compared to Shamir's approach. And it has almost the same overhead as not using any SMC approach for aggregating the partial results. And for the privacy part of our secure aggregation technique, if we do not employ any technique, the values needs to be shared with the mediator, and so there is no need for colluding. The values are known to the mediator, and the minimum number of colluding parties is 1 for identifying the secret values. But for our approach, we need at least k parties, k data holder parties, and the mediator to collude. And for Shamir's approach, we need at least k parties for collusion to identify a secret value. For the evaluation of limited participation of parties, we used multiple features and waveform datasets. We learned classification models by limited participation of parties. We started from 20% of participate, and we continued until 100% of participation. We check the accuracy and F1 scores of the learned models, and we can see that from 40% of participation, we can see that we have more or less the same results for our classification models. So we see that even by having like 40% participation, we will have high performance models. For the overhead, we can see that by increasing the proportion of participating parties, we have a growth in the learning time for each classification model. Here is the learning time, and here is the number of secure aggregations needed for learning one classification model. So we can see that if we limit the proportion of participating parties, we can decrease the overhead, and at the same time we do not have a noticeable loss in the classification performance. So k-PPD-ERT is the extension of Ert algorithm for learning classification models in the scenarios in which data is distributed. We employed a secure multi-party computation technique for aggregating the partial results. Our approach is resilient to collusion of up to k data holder parties and the mediator. And regarding the communication overhead, we can see that our approach has the same communication overhead as employing no SMC approach. And for the limited participation of data holder parties at every round for selecting the best candidate decision node, we can see that by limiting the participating parties, we can decrease the overhead, but we will not have a noticeable loss in the learning performance. Thank you very much for your attention.